Welcome to the deep dive. We take complex source material, unpack it, and give you the insights you need. Today, we're tackling a really persistent issue in AI, this gap between how good large language models are at general stuff and how, well, frankly bad they can be at structured symbolic planning.
It's a fascinating problem, isn't it?
Yeah.
You've got models like GPT, Gemini, Llama. They can write code, they can do math problems, generate amazing text. But ask them to plan a simple sequence of steps in a logical world, like moving blocks around or routing a delivery truck based on strict rules.
They just fall apart.
Exactly. It's not about generating plausible-sounding text anymore. It's about reliable, step-by-step decision-making that follows formal logic. And that usually means using something like PDDL, the Planning Domain Definition Language.
Right, PDDL. And the core difficulty, as you know, is that automated planning itself is computationally hard. We're talking PS-based, complete kind of hard. LLMs are great pattern matchers, but they really struggle with the kind of systematic logical verification needed to make sure a plan actually works.
They generate steps that might seem right individually, but the whole sequence often violates the underlying rules of the domain. They're fluent, but not logical, you could say.
Fluent, but not logical. I like that. So our mission today for you, our expert listeners, is to really dig into a specific framework called PDDL-Instruct. It's a new instruction tuning approach designed specifically to teach LLMs this missing piece, how to do formal logical chain of thought reasoning.
Yeah, the idea is to force the model to really think step by step about things like, is this action even allowed right now? What exactly changes in the world state if I do this? Does the final state actually achieve the goal? It's about adding that logical rigor.
And the headline result here is pretty dramatic. We're not talking small tweaks.
Yeah.
PDDL-Instruct pushed planning accuracy up to, what, 94% on some standard benchmark?
That's right. And for a model like Llama 3.8b, that was an average absolute improvement of something like 66% compared to just using the base model. It's a huge leap.
Okay, a 66% absolute improvement. That definitely changes the game for using LLMs in planning. So let's unpack this. How does PDDL-Instruct actually work? What's the methodology behind these results?
Right. Before we get into the tuning itself, we really need to lay the groundwork, just like the source material does. We have to be clear about what we mean by an automated planning problem in this formal PDDL sense.
Absolutely. For everyone listening, a formal planning problem, let's call it NathCalBall, is defined as a tuple, Langle P, A as 0, G wrangle. It sounds abstract, but it's the basic structure.
Okay, let's break that down.
How large is the set of fluents? These are just the basic facts about the world that can be true or false at any given moment. Think like block A on table or robot arm empty. Together, they define the current state, Cecil dollars.
Got it. Facts describing the state. And $1.
$1 is the set of possible actions the agent can take, like pick up block A or move truck 1 from location X to location Y. It's a finite set.
And each action isn't just a name, it has specific rules, right? Precisely. Each action, say RI, is defined by its own little structure. Sangle pre, del II, wrangle. Are the preconditions the facts that must be true in the current state for the action to be possible?
Like needing the arm to be empty before picking something up?
Exactly. Then ADI are the add effects, the new facts that become true after the action. And RI are the delete effects, the facts that are no longer true.
Okay, preconditions, add effects, delete effects. That defines the action's impact. Then CNI is just the starting state.
The initial configuration of the world, yes. And del A is the goal, the set of conditions we want to be true at the end.
So the whole system evolves based on these actions modifying the state.
Right, through a deterministic state transition function. If you're in state LAI and apply action RI, the next state LI is calculated very simply. You take CAI, remove all the facts listed in LI, and then add all the facts listed in LI. So CCI plus 1 is LI plus 1 comes to LI.
It's purely logical, no probability involved at this level. Given a state and an action, the outcome is fixed.
Completely fixed. Any deviation from that means the model isn't following the rules. And a solution, a plan, is just a sequence of these actions. Langle A's A1 old outs wrangle that transforms the initial state A-lime to some final state dollar where all the dole conditions data hold true.
And importantly, the paper we're looking at focuses on satisficing plans.
Yes, that's a key point. They are looking for any valid plan that reaches the goal. They aren't trying to find the shortest plan or the most efficient one in terms of resources. That's optimal planning, which adds another layer of complexity.
So first, just make it work logically.
Exactly. Get the logical sequence right first.
Okay, so that's the formal setup. Now, why do LLMs, even with their powerful chain of thought abilities, typically fail at this? Where's the disconnect?
Well, studies show that as the plans get longer or the domains get more complex, standard LLM COT breaks down. It can't maintain logical consistency over many steps. The issue is that typical COT relies on the model's sort of internal, maybe semantic understanding of cause and effect.
It generates steps that sound reasonable in English, like, okay, now I'll put the block down.
Right. But it might completely miss a crucial detail, like maybe the table it's trying to put the block on is already full, violating a precondition like clear table.
Mm.
The model's internal self-checking just isn't rigorous enough to catch these formal logic errors consistently.
And attempts to just make the model correct itself didn't really work either.
Often made things worse, actually. The model might try to fix one logical error but introduce a different one, or just get tangled in plausible but incorrect reasoning. Some people even argued code just wasn't suitable for formal planning at all.
Ah, but PDDL-Instruct challenges that directly.
It does. The core argument is that code can work, but it needs to be, let's say, disciplined. It needs instruction tuning that forces it to follow the formal PDDL logic, step by step. And ideally, it needs external verification to keep it honest. It needs to learn to track the state like a symbolic system would.
So it's not just generating a story about planning, it's actually simulating the state transitions internally, following the rules.
That's the goal. Achieving that strict logical coherence, making sure every state truly follows, from Psi1-aller and action-allers, according to the rules. That's the nut they're trying to crack.
Okay, let's get into the PDDL-Instruct framework itself. It's a two-phase training process, right? Phase 1 builds a foundation, and Phase 2 adds this external logic enforcement.
That's a good way to put it. Phase 1 is called initial instruction tuning. The idea here is to take a pre-trained LLM and quickly get it familiar with the language and structure of PDDL planning problems. They use standard instruction tuning methods, basically showing the model examples of PDDL domains and problems, paired with detailed explanations of how to solve them.
So showing it good examples, but the really clever part of Phase 1 seems to be that they didn't just show it perfect plans.
Exactly. This is crucial. The training data for Phase 1, let's call it DDL-1, deliberately includes examples of incorrect plans. This forces the model to learn verification skills right from the start. It sees not only success, but also failure, and importantly, why things failed.
And they categorize these failures. What kinds of errors did they inject?
They focused on 4 key types of logical mistakes. First, unsatisfied preconditions. Trying to perform an action when the necessary conditions aren't met, like trying to stack block B on block C when block C isn't clear.
Okay, standard precondition violation. What else?
Second, incorrect effect application. The model tries to update the state after an action, but gets the add or delete effects wrong. Maybe it forgets to delete a fact that should no longer be true, or add something spurious.
Right, messing up the state update.
Third is frame axiom violations. This is a bit more subtle. It's about ensuring facts that aren't affected by an action remain unchanged. If I move block A, the status of block Z shouldn't magically change unless the action explicitly affects it. LLMs can sometimes struggle with this persistence.
The common sense of what stays the same.
Precisely. And the fourth category is just goal state failure. The plan executes fine step by step, all actions are valid, but the final state just doesn't satisfy all the required goal conditions.
So by training on both good plans and these specific types of bad plans, the Phase 1 model gets an initial grounding in logical checking.
That's the idea. Build that foundational understanding of PDDL logic.
Which then sets up Phase 2, logical code instruction tuning. This sounds like the core innovation, where the external verification comes in.
It is. They take the model that finished Phase 1 and put it into this feedback loop. The model generates a plan, but not just the actions it generates, a detailed step-by-step reasoning chain, like Langle E0, A1, S1 wrangle, then Langle S1, A2, S2 wrangle, and so on, justifying each step.
A full trace of its thinking.
Exactly. And this entire reasoning chain is then passed to an external symbolic verifier.
And that's VAL.
Yes, VAL, the standard, widely used validator for PDDL. VAL doesn't care about the LLM's explanation, it just checks rigorously. Is action $A actually applicable in state sitter according to the domain rules? If so, does applying $A really result in state sitter dollars?
So it's an objective mathematical check of every single step. This avoids the problem of the LLM just kind of convincing itself it's right.
Precisely. It bypasses the unreliability of LLM self-correction. Research shows LLMs aren't good enough yet at robustly verifying their own complex logical reasoning. VAL provides that external ground truth. The feedback from VALs is then used to further fine-tune the model.
It forces the model's internal code process to align with the actual formal logic defined in the PDDL.
That's the mechanism. And critically, they tested two different types of feedback from VAL, which relates to their research question too.
Okay, what were the two types?
The first was simple binary feedback. VAL just says, yep, this step is valid, or nope, this step is invalid, true or false.
I'll be basic signal.
Very basic. The second type was detailed feedback. This is much richer. If a step is invalid, VAL doesn't just say no, it explains why. It might say invalid because precondition, arm empty, was not true in state 0, no, or invalid because effect, holding block A, was incorrectly added.
Ah, so it provides specific actionable diagnostic information. That sounds potentially much more useful for learning.
That was the hypothesis, and as we'll see, the results bear that out strongly. It gives the model a much clearer signal about what specific part of its reasoning went wrong.
One last point on the methodology. They were still focused just on getting a valid plan, right? Not the best plan.
Correct. The design explicitly avoids trying to optimize for plan length or efficiency, what they call progressive refinement. The entire focus of this two-phase tuning is on achieving logical coherence, making sure every single step follows the domain rules and the final plan reaches the goal. Getting that fundamental correctness locked down was the priority.
Okay, let's dive deeper into phase 2. This two-stage optimization process seems really key. It's designed to teach the model the logic and make sure it can actually solve the planning tasks without losing the logic it just learned. How does that work technically?
Right, it's quite elegant. First, remember the goal is logical coherence in the chain of thought Z next street. Each intermediate state must logically follow from the previous state, Z at A doc, and the action on X. The optimization has two stages that reflect this.
Stage 1 is the reasoning chain optimization. This uses a higher learning rate to delta off to 1. What exactly is the loss function reasoning minimizing here?
Stage 1 is all about drilling the logical rules into the model. The parameters to TART are updated using that relatively high learning rate, delta 1 times 10 to 5. The loss reasoning is calculated not on the whole plan, but on each individual step, each Langle, SI1 at I, side-wrangle triplet within the reasoning chain. It uses the feedback 5 Taylors from VLL for that specific step.
So it penalizes every flawed step the model takes in its reasoning.
Exactly. It's a very granular penalty. The actual loss for each step, less step, has two main parts.
Okay, what's the first part?
The first is a state distance measure. Does the CDI? This compares the state CD cons that the model thought it reached with the state deller that VAL determined is the correct state after applying action data. The metric is the symmetric difference, yellow triangle set.
Symmetric difference. So it's just counting how many facts are wrong, like facts the model included but shouldn't have, plus facts it missed.
Precisely. It's a direct measure of how badly the model miscalculated the state transition. If it gets the state perfectly right, this distance is 0.
Okay, that makes sense. What's the second part of Lambda?
The second part incorporates the VL feedback more directly. It's lambda feedback, SLML feedback. This is where the detailed error information comes in, especially if you're using the detailed feedback type.
And this lambda uses those specific penalty weights we talked about earlier.
Yes, this is where those carefully chosen weights apply. There's a weight, alpha precon, $1 for precondition violations. There's alpha effect, 1 partile for getting the adelete effects wrong. And interestingly, the weight for failing to satisfy the goal conditions, alpha goal, is set higher at $1.55.
So violating rules is bad. But failing the overall objective is slightly worse, even during the step-by-step tuning.
That seems to be the rationale. It puts a bit more emphasis on the ultimate goal. The overall feedback term is scaled by lambda feedback, which they set to 0.1. This balances the influence of the direct VLL feedback penalties against the state distance term.
So stage 1 aggressively pushes the model, step by step, to predict correct state transitions and respect preconditions, using a relatively high learning rate.
That's the essence of it. Build that fundamental logical machinery.
Then comes stage 2, end task performance optimization. The focus shifts here, right? And the learning rate drops.
Exactly. Stage 2 takes the parameters, the TART, that have been improved by Stage 1's reasoning focus and fine-tunes them further to task boot plus one other using a much lower learning rate. Delta 2 yields 5 times 10.6.
Why the lower learning rate?
The idea is to gently optimize for overall task success, generating a complete, valid plan without disrupting the fine-grained logical coherence learned in Stage 1. You don't want to suddenly make the model forget how to follow rules just because you're pushing it harder to find any solution.
Makes sense. Preserve the gains. What does the loss function dollar look like for this stage?
All final operates at the level of the entire plan.
Mm-hmm.
Its main job is to strongly penalize generating an invalid plan. It has a big penalty term, IV dollar beta. Here, IV dollars is just an indicator function that's 1 if the final plan is invalid, as judged by VAL, so V8 and otherwise, and beta dollars, a large penalty weight, set to 2.0.
So if the plan is invalid, WHAM, big penalty.
Huge penalty. It really drives home that invalid plans are unacceptable. This is combined with a standard binary cross-entropy BCE loss, scaled by alpha dollars 5 dollars ones, which helps the model learn to predict whether its generated plan will be valid or not.
Okay, so stage 2 takes the logically improved model from stage 1 and uses a gentler learning rate with a strong penalty on overall failure to make sure it reliably produces correct end-to-end plans.
That's the two-stage process. First, learn the rules, then learn to win using the rules.
And you mentioned the need to handle longer sequences for these cochenes.
Right. A practical but important detail. Because the COT includes the states, actions, justifications, maybe even feedback, the sequences get very long. They had to double the maximum sequence length the model could handle to 4 theory 96 tokens.
That's a significant increase in context window needed.
Absolutely necessary to accommodate the verbose logical reasoning. They also experimented with a number of feedback loops in phase 2, the parameter kata, testing both 10 and 15 loops to see if more refinement cycles held.
All right, let's get to the results. How did PDDL-Instruct actually perform? They used PlanBench, which is a standard benchmark suite, right? And tested both Llama 3 and GPT-4.
Correct. PlanBench provides standardized tasks across different PDDL domains. Using both Llama 3 8B and GPT-4 helps show if the benefits are general or specific to one model architecture. They focus on 3 main domains, each with 100 test problems.
Let's quickly recap the domains. First, blocks world.
Classic AI planning domain, stacking blocks on a table or other blocks. Relatively simple actions, good for testing basic logical correctness.
Then logistics.
Much more complex. Involves moving packages between locations using trucks and airplanes. Requires reasoning about connectivity, capacity, multi-step sequences. Much larger state space, longer plans, usually.
Okay, complexity increases. And the third one was mystery blocks world.
Yeah, this one's designed to be tricky for LLMs. It's basically blocks world, but all the names for objects and predicates are replaced with meaningless symbols like predicate X, object A, object B.
Ah, so the model can't rely on the English meaning of stack or on. It has to use the formal PDDL rules.
Exactly. It's a test of pure logical generalization, removing semantic clues.
And the main metric was just plan accuracy. Did VAL say the final plan was valid and achieve the goal? Simple pass-fail.
Simple pass-fail, yes. Very stringent.
So let's hit RQ1, overall performance. What were the numbers, particularly for the best configuration they found using detailed feedback and the higher iteration count, TED of $15?
The results were pretty remarkable. For Llama 3 8B, it achieved 94% accuracy on blocks world. That's very high. On the more complex logistics domain, 79%. And on mystery blocks world, the really tough one, it hit 64%.
Wow, 64% on mystery, considering how badly baseline models usually do there.
Exactly. Compared to the baseline Llama 3 model without PDDL-Instruct, this represented an average absolute improvement across the domains of 66%. That's a massive jump.
66% absolute average gain.
Okay. And how did GPT-4 do with the same setup?
GPT-4 also saw huge gains, though slightly lower than Llama 3 in this setup. It got 91% on blocks world, 78% on logistics, and 59% on mystery blocks world. Still a very significant improvement, averaging around 61% absolute gain over its baseline.
The fact that it works so well on both Llama and GPT models is strong evidence for the method itself, not just the underlying model.
Absolutely. It suggests the instruction tuning framework is the key driver here, not just throwing a bigger model at the problem. The training signal seems to be what was missing. Okay, now RQ2, the impact of feedback quality. This is where we compare the simple binary feedback versus the detailed feedback. Did the richer signal actually make a difference?
A huge difference. Detailed feedback consistently outperformed binary feedback. This held true for both Llama 3 and GPT-4 across all 3 domains.
Where is the difference most obvious?
Well, it was most pronounced in the hardest domain, mystery blocks world, which makes sense. That's where the most complex logical reasoning is needed. For Llama 3 on mystery, using detailed feedback resulted in an accuracy that was 15 percentage points higher than using just binary feedback.
15 points, that's substantial. Just from getting told why a step was wrong instead of just that it was wrong.
It really underscores the value of specific diagnostic error signals for learning complex logical procedures. The detailed feedback provides that crucial guidance that simple invalid doesn't.
And did running more feedback loops, increasing data to the dollar from 10 to 15, help?
It did, consistently. On average, going from 10 to 15 iterations gave about a 4.3 percentage point boost in accuracy. But interestingly, this improvement was much more significant when detailed feedback was being used.
So More iterations are only really helpful if the feedback signal itself is informative enough.
Seems that way. More loops of processing a weak signal don't help as much as processing a rich signal, even for fewer loops. But processing a rich signal for more loops helps the most. It points again to the quality of the feedback being critical.
Okay, finally, RQ3 looked at cross-domain generalization. Performance obviously varied by domain difficulty.
Yes, Blocks World was easiest, then logistics, then Mystery Blocks World was the hardest, as expected.
But the relative improvement, how much better PDDL-Instruct made the models compared to their baseline, that tells an interesting story, especially for Mystery Blocks World.
That's the most compelling part, I think. The baseline Llama 3 model, just out of the box, scored a miserable 1% accuracy on Mystery Blocks World. It basically couldn't do it at all.
1%. Essentially guessing, or worse.
Pretty much. But after training with PDDL-Instruct, using detailed feedback in head F55 towers, that jumped to 64%.
From 1% to 64%. That's a 64-fold increase in performance on the hardest, most logic-dependent task.
It's a staggering difference, and what it strongly suggests is that the model, through this rigorous training, has actually learned something about the underlying structure of PDDL planning, precondition checking, fact applications, state tracking, independent of the specific names or semantics. It's not just pattern matching English anymore.
It shows the method is most valuable exactly where LLMs are weakest in complex, abstract, purely logical reasoning scenarios.
Exactly. The harder the logical challenge, the more this kind of explicit, verified reasoning training seems to pay off. So pulling it all together, PDDL-Instruct really does seem to be a successful strategy for bridging that gap between LLM fluency and symbolic logic. The key is enforcing that logical coherence using the external VAL verifier during training. It effectively combats that tendency of LLMs towards unfaithful reasoning, generating plausible but logically flawed steps.
Because VLL calls it out every single time.
Every time. It forces the model's internal representations and processes to align with the formal PDDL semantics.
Now, the researchers were commendably upfront about the limitations of this current work. What are the main caveats, and where do they suggest future research should go?
Well, the big one we already touched on is optimal planning. Right now, it just finds any valid plan. A major next step is to extend this to find high-quality plans, maybe the shortest ones or ones that minimize resource use. That involves adding cost functions and likely more sophisticated search or learning strategies.
That seems like a natural, but probably quite challenging next step. What else?
Another limitation is the PDDL coverage. For this initial work, they used a restricted subset of PDDL features. They didn't include things like conditional effects, where an action's effect depends on the state, or durative actions, actions that take time, or numeric fluence. Real-world PDDL often uses these.
So, expanding the framework to handle more expressive PDDL features is needed for broader applicability.
Definitely. It's crucial for tackling more realistic planning problems in areas like robotics or complex logistics.
And then there's the reliance on VAL. Is the long-term goal to get rid of the external verifier?
That's a fascinating and ambitious direction they point towards, self-verification. Could LLMs eventually become reliable enough to validate their own logical steps, internalizing the role of VAL? That would be a huge step towards more autonomous reasoning systems. Right now, VAL is essential, but maybe not forever.
Internalizing the logic checker. Interesting. Any other refinements suggested?
One more is moving beyond the fixed number of training iterations at $. They suggest exploring dynamic iteration control. Maybe the system could learn to determine how many feedback loops are needed for a given problem's complexity instead of just running 15 loops for everything. That could make the training much more efficient.
Okay, those are clear directions for improvement. Let's talk broader impacts. Assuming this line of research continues successfully, what are the potential upsides?
The potential upsides are significant, especially in areas where reliable, automated decision-making is critical. Think healthcare robotics, autonomous driving, managing complex supply chains or power grids. Having AI systems that can generate plans and provide a verifiable, logical trace of how they arrived at them. That increases both interpretability and trust.
You can actually audit the AI's reasoning against the formal rules.
Exactly. It helps bridge that gap between powerful but opaque neural networks and verifiable symbolic systems. It could lead to safer, dependable AI in critical applications.
And the flip side, what are the risks we need to consider as LLMs get better at planning?
Well, the obvious risk is over-reliance. If these systems become very capable but still have edge case failure modes, deploying them in safety-critical situations could lead to catastrophic outcomes if something unexpected happens that wasn't covered in training or verification. The hybrid nature also makes debugging harder is the error in the LLM's generation or the interaction with the verifier.
And the potential for misuse.
That's always a concern with more capable AI. Enhanced planning abilities could potentially be used for malicious purposes, devising complex multi-step attacks, strategic manipulation, or coordinating autonomous harmful actions. So, mitigation strategies like robust external oversight, keeping humans in the loop, and designing strong safeguards around their use are absolutely essential. Hashtag tag outro, Dua.
So we've taken a pretty deep dive today into PDDL-Instruct, seeing how it blends the generative strengths of LLMs with the logical precision of symbolic verification. The key takeaways seem to be the importance of instruction tuning with both good and bad examples, the dual-stage optimization balancing logic and performance, and especially the power of detailed diagnostic feedback from an external source like VAL.
Absolutely. It really highlights this ongoing theme in AI that while neural models are incredibly powerful at learning patterns and generating possibilities, formal symbolic methods still hold a vital role as the arbiters of logical truth and consistency. PDDL-Instruct is a practical demonstration of how these two paradigms can work together effectively.
And for you, our listeners, grappling with these complex systems, here's a final thought to chew on, sparked directly by these findings. RQ2 showed decisively that detailed diagnostic feedback was far superior to simple binary feedback. So could it be that the next major breakthrough in getting LLMs to reason logically isn't primarily about bigger models or fancier architectures, but actually about inventing much more sophisticated, granular, and informative ways to provide error signals during training?
That's a provocative question.
PDDL-Instruct's success certainly suggests that the path to logical precision might lie more in the quality and clarity of the correction signal than purely in the generative model itself. Something to think about.